Welcome back to another Explainer. Today, we're diving straight into the fascinating, totally hidden mechanics of marine propulsion systems. We're going to bridge centuries of quirky history with some seriously modern engineering marvels. You know, we see these massive cargo ships moving across our oceans all the time, but the actual mechanics of how they do it, that remains almost entirely out of sight, buried way down deep beneath the waterline and heavy steel bulkheads.
Which brings us to an incredible question. Just how exactly does a spinning blade move hundreds of thousands of tons of steel and cargo through a dense medium like water? I mean, it's mind-boggling. To truly grasp the sheer scale of moving a modern Leviathan like that, we actually need to hit rewind. We've got to look at the surprisingly messy, kind of trial-and-error history of how we even figured out the correct shape of the propeller in the first place.
So here's our roadmap for this explainer. 1. The quest for propulsion. 2. A fortunate broken blade. 3. The anatomy of the transmission. 4. The mighty thrust block. And 5. Maintenance and alignment. Let's get right into it.
Section 1. The quest for propulsion. Let's kick things off by tracing the winding path of marine invention, which actually started way, way before anyone even conceived of a modern cargo ship or a diesel engine. It's wild to see how this idea evolved over millennia. I mean, we're talking about starting with the water-lifting screw pump conceived by Archimedes way back around 250 BC, then jump ahead to Robert Hooke's horizontal watermill in the late 17th century. Centuries after that, you have John Ericsson testing these really complex contra-rotating wheels on the River Thames, right before Francis Petty Smith finally launched his breakthrough ship in 1839. This was literally a centuries-long puzzle. What's truly fascinating here is how wildly different the early theories were. Look at Hooke's design from 1683. He originally modified a windmill to measure water currents, using these 4 flat rectangular blades, and basically hypothesized, hey, maybe this could drive a ship. Then contrast that with Daniel Bernoulli's prize-winning wheel from 1752, which was intended to be driven by a steam engine. Even the absolute greatest scientific minds of Europe were totally divided on what a marine propulsor should actually look like. Moving on to Section 2, a fortunate broken blade. Now, you might think the greatest leap in maritime engineering came from some calculated mathematical formula. Actually, it was a complete, totally fortunate accident. Picture this. It's 1837. Inventor Francis Petit Smith is running canal trials on his 6-ton prototype boat powered by a steam engine. He's using a wooden propeller shaped like a super long 2-turn Archimedean screw. Right in the middle of the trial, the wooden propeller strikes something underwater and literally breaks in half. But instead of the ship failing and sinking, this happy accident miraculously made the ship surge forward. It proved, completely by chance, that a shorter blade was vastly more efficient than a long continuous screw. It changed propulsion design forever. Smith, being a smart guy, learned from this. He took his new single-turn screw and placed it within the deadwood of the ship. That's the solid timbering at the stern, tucked just ahead of the rudder. This specific placement protected the propeller and vastly improved the steering dynamics. It was such a game-changer that it finally convinced the highly skeptical British Admiralty to officially adopt screw propulsion for their naval vessels. All right, Section 3, Anatomy of the Transmission. Let's fast forward to the modern era and tear down the mechanical reality of how that broken wooden blade evolved into today's massive, highly engineered transmission systems. To understand the physics of how we move these absolute giants today, think of an airplane wing. The modern propeller blade acts exactly like an aerofoil, just underwater. Because of its specific curve, it increases the velocity of the water at the top of the blade, which drops the pressure at the back. This pressure difference exerts a massive force perpendicular to the blade. And boom, you've got incredible forward thrust. This builds what we call the path of power. It's essentially a sequence of heavy, meticulously machined steel shafts, all connected by bolted couplings. The journey starts at the main engine flywheel, transfers to the thrust shaft, moves down the intermediate shaft, and finally hits the propeller shaft. This continuous line is the literal backbone that transfers raw rotational energy from the belly of the ship all the way out into the ocean. But you can't just have gigantic steel shafts spinning in midair. Along this path, they rely on some incredible support systems. We're talking about precisely aligned intermediate bearings to shoulder the heavy shaft load. Then you have the stern tube securely holding the outer shaft, which is lubricated by either oil or seawater, while the massive stern frame carries the immensely heavy overhung mass of the solid metal propeller itself. It's a heavy-duty balancing act. Section 4, the mighty thrust block. Now we reach the absolute heart of the system, which solves the ultimate mechanical problem. Think about it for a second.
If the propeller is pushing millions of pounds of water backward, well, the water is pushing the propeller forward with equal force. So how do you stop that massive force from just ripping the main engine right off its mounts? Let's trace the reverse path of thrust. The spinning propeller grabs the water and violently pushes the shaft forward. But before that destructive force can reach the engine, a component called the thrust block steps in. It intercepts that raw forward power and redirects it straight into the sturdy steel hull, literally pushing the entire ship through the water.
So how does the thrust block actually survive this punishment? Inside the casing, you have stationary thrust pads and a spinning thrust collar on the shaft. But here is the absolute magic of it all. All of this world-moving force rides entirely on a hydrodynamic fluid film wedge. That's just a fancy way of saying a microscopic layer of pressurized oil. The metal parts never actually touch. Millions of pounds of force rely entirely on this tiny, tiny sliver of fluid. Crazy, right?
That brings us to Section 5, maintenance and alignment. Because these operating forces are so incredibly intense, keeping these leviathans moving requires an almost mind-boggling level of precision maintenance. Periodically, the engineering crew has to check the shaft alignment. And to do this, they literally hoist the entire steel shaft column inside the ship using hydraulic jacks. They slacken the bolts, pump the jacks, and very carefully plot the lift distance against the load weight on a graph. They're looking for the exact perfect moment the shaft floats free, just to ensure every single bearing down the line is sharing that massive burden equally.
But out of all the incredibly complex measurements taken down in the engine room, there is one number that dictates the stakes for the entire vessel: 0.1. 0.1 millimeters. To ensure that hydrodynamic fluid wedge we just talked about is still protecting the engine, engineers insert a feeler gauge into a wear groove on the thrust collar. If a 0.1 millimeter gauge, which, by the way, is roughly the thickness of a single human hair, can't slide into that groove, it means the white metal on the bearing is wearing away. The magic film is failing, and a grueling overhaul protocol must begin immediately.
And trust me, this is no quick oil change. This grueling overhaul involves stripping off the protective shields and the lube pipes. The crew has to use heavy-duty hydraulic jacks just to lift the top half of the bearing casing. Then they mount a special segment tool and painstakingly, slowly turn the colossal main engine itself just to slide the heavy thrust segments out one by one for inspection and replacement. It's a massive job.
So, as we wrap up this explainer, we can clearly see that the thrust block is the true unsung hero of global shipping. It just sits there silently in the belly of the ship, acting as this crucial mechanical bottleneck. It takes all those quirky trial-and-error discoveries from 19th century inventors like Hooke and Smith and safely translates that raw, destructive physical force into the forward momentum that quite literally drives our modern world. I want to leave you with this final thought to ponder. Next time you're out looking at the ocean and you see a massive cargo ship effortlessly gliding across the horizon, think about the incredible hidden mechanics operating just beneath the surface. Think about the fact that all of that immense scale, millions of pounds of force, relies entirely on an invisible, microscopic layer of oil and a fraction of a millimeter of steel. Thanks for joining me on this explainer, and keep questioning how the world around you actually works.